Okay, so hello everyone, thanks for coming. So I'm Michał, and saying two things about myself. So I'm a PhD candidate at the AGH University in Krakow at the Department of Computer Science, and I'm also working for the California startup which is using various AI solutions for driving assistance. But today's talk is not going to be about safe driving or autonomous driving. It will be about quite a research-oriented topic, that is posterior collapse. Because it's research-oriented, I'm going to only scratch over the surface. So at the beginning, I will introduce variational autoencoder, quickly summarize it. Later, I will introduce the posterior collapse concept. I will show you how it manifests. Later, we will talk about what we can do with this posterior collapse, and at the end, some further readings. So, when it comes to variational autoencoder, so first introduced it in the paper by Dirk Kingma and Max Welling. So formally, this model basically comprises so-called latent space, and this latent space contains some latent vectors, and from the model, we are having probability distribution over this latent space. It's called the prior. Next, we are having some deterministic mapping, which is no surprise, is a neural network, which encodes this latent vector Z into our data space. Latent is called because it's unobserved. When we are learning such models, we are not observing in our training data set this Z, and this Z affects our data sample over the mapping F. And this mapping F is used to define generative probability of X given Z. So basically, as I told, the mapping is a neural network, and if we take the simplest case that our decoder, our generative probability is Gaussian with identity matrix, then basically our neural network F encodes only the mean parameter of such Gaussian. Obviously, the simplest choice of the decoder that is a Gaussian is not, this is not fixed. One can use much more powerful decoder, for instance, coming from autoregressive family, like gated pixel CNN, but we will stick to the simplest case. Okay, and when it comes, we can easily generate samples from such model. Basically, as I told, we are sampling from our prior. We are sampling latent vector from our prior. Later, we are using our neural network, and because this is a simple generative probability, then basically we are obtaining our data sample. But the name autoencoder is used non-coincidentally here. So besides this generator, besides this decoder, we also need some encoder. That is something that is mapping from our data space, from our X's into latent space, into our Z's. And here is the full model of variational autoencoder. So here we are having an encoder which is representing so-called posterior probability of Z given X. Basically, technically, this encoder is giving us the mean and covariance parameters of the Gaussian distribution, because we are assuming usually that this posterior has the form of Gaussian. Later, from these parameters, we are obtaining our code Z via so-called reparametrization trick, but technically we are just sampling from this, from Gaussian distribution, and at the end, our decoder is again mapping our latent code into the observable space. So basically, that's how we are obtaining our reconstructions. So this is on the next slide. You see exactly what I'm talking about. So once again, if we want to reconstruct our data, we are calculating the posterior parameters, later latent code Z, and through the decoder we are having our reconstructed sample. So, okay, now we can move to posterior collapse. So basically, I've prepared a couple experiments to show you this concept, and for these experiments I used so-called celebrity faces dataset, which contains small images, 64 by 64, 3 channels images. It has over 200K examples. So basically I split this data set into the training one and test one in such ratio, so for training 150K. And I created a simple variational autoencoder where encoder has a simple architecture, which basically after the input we are having a series of 5 convolutions and nonlinearity. And at the end there is a fully connected layer with 64 units in order to 32 for mean and 32 for covariance. And basically the coder is the inverse of encoder, where from this 32-dimensional latent code I'm deriving the final object by applying some series of transposed convolutions. Okay, and now please take a look at the reconstruction and data generation. So basically take a look. So this position corresponds to this original image and this is reconstructed one. So in most cases some very basic features are saved, but definitely we would like to have more detailed reconstructions, okay? So now take a look at the generation, data generation. So again, we are not here, we are sampling this latent code from prior, from standard normal. So, and we are passing over the decoder. So as you can see, basically this reconstruction samples look very similar to these generated samples. And if you take a closer look at particular examples, for instance, Conan the Barbarian gets reconstructed into something like this. Well, probably you would like to have some better reconstruction. And for instance, the other two examples also very far from being perfect. So what happens here? Although the decoder is giving us the samples which resemble our natural face images, it's basically losing all of the peculiar features of each particular example. So one can say that the decoder is ignoring the latent code, which is again calculated from the original example. And basically for now we can introduce the simple definition of posterior collapse is that basically the decoder, the latent code which is supposed to contain all of the compressed features of our original example, that this latent code is being ignored when during the decoding process. Okay, and in order to answer why is that, we need to dig deeper how these variational autoencoders are being trained. So basically, like in other neural networks, we are adopting so-called maximum likelihood estimation procedure. So basically, we are looking for such parameters of the neural network. Here, we are having two neural networks, encoder and decoder. So basically, we are looking for such parameters that the probability assigned by this model is as high as possible. So basically, it's summarized in this formula. But here's from this model we are having prior P of Z, we are having generative probability, so it might seem that we can calculate the probability of our training examples, but unfortunately we have to do the integration, and unfortunately we have to do the integration over Z variable, where the Z variable appears in the decoder in a very complicated way, so such integration is unfortunately infeasible. So we have to do something different, and fortunately we can introduce the function which is tractable to compute, and for each of the parameter theta for each example is smaller than the original log likelihood, and that's why we are calling it a lower bound. So the full name of it is ELBOW, in other words, evidence likelihood lower bound. And if this ELBOW is close enough to our original data log likelihood, then we can hope that if we find good parameters for this ELBOW, they will be also a good parameters for our original criterion, right? Okay, and it appears that, as I told, this ELBOW is tractable, and it's the formula for it. It might look complicated, so at the beginning, so first term is some expected value. Later, there is so-called DKL term. This DKL term stands for Kullback-Leibler divergence, and it measures the similarity between two probability distributions. And it appears in that appears that in this case it measures the probability between this posterior Q, which is modeled by the encoder, and between the prior. And if you take a look at this term, basically it can be called like a reconstruction term, as if it's supposed to be fine, if it's supposed to be big enough, then basically it seems that model has to do a good reconstruction, do a good job in reconstructing our examples. So basically from the latent code samples from this posterior, this probability has to it probably has to assign relatively high values of probability for the original value axis. In case of simple Gaussian decoder, it appears that this is a simple L2 loss between the reconstructed value and the input value. So, okay, and let's take a closer look. How does this DKL term affect the whole training process? So basically, the encoder during the learning is proposing some latent code, and without this DKL criterion, it would propose such latent code which is lying in a space that the decoder can conveniently reconstruct our sample from. And this DKL term acts as a kind of regularizer, which is pushing this latent code Z into the prior P of Z, which again, prior P of Z is a standard normal, which means that this is mean equal to Z, vector of zeros, and identity covariance matrix. So basically it's pushing, this DKL is pushing our latent code into the hypersphere center at 0 with radius 1. And unfortunately, in many cases, this DKL term is pushing too much, our latent code. So basically this latent code becomes indistinguishable from these samples from the prior. And we are saying that the posterior collapses into the prior. So this is the story behind the central concept of this presentation. And okay, and why is it a problem? Because take a look. If this term becomes very small, then basically posterior Z given X becomes almost like a prior P of Z. It means that this conditioning on X drops off. So basically now the code becomes independent of our data sample, which is very bad, as we require from our Q to learn actually the representation of our X, right? So what we can do with it? So the first thing, because in the original elbow formulation, there is this reconstruction term and DKL term, but we can obviously, that's a simple idea, but honestly very useful, that we are assigning some weight into this DKL term. So basically, we can vary how much to our final optimization criterion to how important is this DKL term. And because when this term is too important, then this posterior collapse happens, it's reasonable to introduce beta smaller than 1. And when beta is smaller than 1, then still this formulation is still a lower bound, as DKL gives us the guarantee that it's non-negative. So basically here we are adding something smaller with smaller weight, and we are still having an elbow. Just this elbow is less tight. Yeah, when the beta is greater than 1, it's this function is not guaranteed to be a lower bound, but this is the other story. By the way, this concept was introduced in the paper the model beta VAE, and in this paper it was introduced in this publication, where the purpose of such model was slightly different. It was about learning this entangled representation, but this is not a topic of today's presentation. But I strongly encourage you to consult this paper. Okay, so what happens later? Let's introduce beta very small, something like 0.01. Okay, so 10 to power minus 2. And take a look at the reconstructions. Okay, so definitely it looks much better. These reconstructing samples are much more similar to the original ones. For instance, let's take it, oh, Conan the Barbarian is here. Yeah, it's much better than previously. But when it comes to data generation, something like this happens. And this is no surprise, because if we are assigning very small weight to our DKL term, then usually these latent codes are far from the prior, and we are generating data from this prior, okay, by sampling z's from prior and later passing through the coder. So unfortunately, data generations are very poor. Okay, so let's increase into 0.1. So reconstructions are still good, but if you take a look at the data generation, it's better, but it's definitely far from perfect. Okay, so let's go higher, 0.25. Yeah, still reconstructions better than if beta is equal to 1. And generation looks quite fine. So basically, the purpose of this of showing you the results for various values of beta is that although this concept of beta VAE is quite simple, then for our data set we can usually choose some reasonable beta value that this latent codes won't be ignored, and still our generation process will give reasonable results. Okay, so the next solution. Let's introduce modified variational autoencoder, so-called vector quantized VAE. It was first introduced by Aaron van der Oort team. It's summarized in the paper Neural Discrete Representation Learning. So here basically, because in the traditional VAE, our our latent vector is continuous, right? This is, for instance, 32 values which are potentially from minus to plus infinity. So here, our z becomes discrete. So basically here, our latent representation is a two-dimensional grid of discrete symbols from 1 to k. Okay, and how this model works? So at the beginning, we have encoder, which at the end is giving us some convolutional volume. And here we are maintaining some vectors, which we are calling embeddings. And here, at each spatial position of the encoder's feature map, we are comparing with L2 distance. We are comparing how close this vector is from our embeddings. And the index of the vector which is the closest one is being prescribed here. So for instance, here it seems that the closest vector to this one is E1. Okay, and later, during the decoding process, what we have to do, we are preparing again the kind of 3D volume by doing the inverse, by prescribing these embedding vectors according to the indices which are contained in our grid Z. So here the vector E1 is being prescribed on the input of the decoder, and later the decoder is some convolutional architecture which is giving us the final example, right? Now the question is, okay, how much time? Okay, the question is, how do we train such a model? So, okay, the first step, we are using reconstruction laws. But if you look at it closely, then unfortunately it's impossible to propagate gradients over Z, right? Because they are discrete. So you have to rely on some tricks. So basically, okay, in general, this loss function, besides reconstruction, contains other components, which I will explain later. But here, it's impossible to backpropagate gradients on the encoder's input. So what we are doing, we are basically prescribing the gradients from decoder's input into encoder's output. That's the first thing. But in this scenario, we are leaving our embedding vectors alone. So basically, we are not learning them. So the second term is responsible for learning these embedding vectors. And we are doing it by bringing them close to the encoder's output. This SG stays for stop gradient. So if anyone, it basically, during the forward time, it acts as an identity function, but it prevents from the gradients being propagated through this node in the graph. If we are talking about in the context of, for instance, TensorFlow. So in TensorFlow, this is TF stop gradient function, which is doing exactly this. And also, there is a third term, so-called commitment loss, which is, by the way, there is an error. It should be stop gradient of E, which basically prevents these embedding vectors to grow too much. So, but I strongly encourage you to consult this paper. Okay, so this is so we are applying some tricks in order to train the model for reconstruction. But there is also the very important task of data generation. So what we can do with it? Because Z is discrete, then we can apply some very nice machinery, which is called a family of autoregressive models, which originally were developed to work over the pixel space, but basically they are leveraging this property of joint random variable. Basically, such a joint probability decomposes into such conditional probabilities, given we are establishing some order between the dimensions of Z. And we can be modeling such conditional probabilities via CNN. So this is the idea of models like autoregressive models like Pixel CNN++, or Pixel Snail. And the nice thing here, so basically we are fitting such autoregressive model to our prior Z. And because Z is usually a grid of 16 by 16, then this is not that painful, because in general, if we are working on pixel space, if we are working on images having the resolution over 100 by 100, such models, autoregressive models, are very difficult to train. Sampling from it takes ages because we have to be sampling sequentially pixel by pixel. But here is not that painful. And and where we are taking our data to fit such a prior. So basically, if we already have our vector quantized via trained with reconstruction laws, then we can use it to propose the latent samples from our data set with this model. So basically, such prior is being fitted with the data pre-processed by the encoder. Okay, and let's take a look at the results. Here's, for instance, the reconstruction. So basically, the original resolution is 64 by 64, and I've chosen the latent grid to be 16 by 16, basically 20 symbols. So in order to encode one of the possible 20 states, we need only 5 bits. So basically, the latent space is quite small, even smaller than the original VAE I was showing you previously, with latent space equal to 32. And as you can see, the reconstructions are quite fine. Although being quite blurry, definitely the content of each sample is being saved as well as together with various peculiar features of the face. Okay, and how about data generation? Something like this. Definitely some artifacts which are undesired, but more or less these images look quite sharp, and some samples are indistinguishable, I would say, by human. And the architecture which I used for this autoregressive, I took Pixel CNN architecture with quite a big one, so 12 layers, 64 filters, quite a big receptive field. Remember that we are working over data 16 by 16, so this model is quite complex given our data. And okay, and the final thing is the delta VAE, where basically what we are doing here, we are explicitly imposing a constraint on our DKL term. So our DKL term is guaranteed to not to be smaller than certain value. This constraint is delta, and we are giving it from the outside. But unfortunately, I was unable to train this delta VAE. The reconstructions and generations were almost very similar to each other. So basically, I'm not even showing it to you. Maybe it's possible that I don't know decoder was not sufficiently powerful or something like this. Okay, and here is some further readings. Okay, and from my side, that's all. Thank you.
Thank you, Michael, for your presentation. We got a couple minutes for 2 questions before the break, so go ahead.
Hi, thank you for your talk. I only have a short technical question because you said you had 200,000 of small images. So how long it took you to train the models? Like how many epochs and how much time it was on which?
Yeah, when it comes to training protocols, so basically, because these are 64 by 64, and I had the luxury of having access to Volta V100 cards, so basically I trained for 60 epochs, I trained for half an hour, the whole data set, so basically it was very fast. But even on much less powerful cards, it still would be very fast, as our encoder this is convolutional architecture, the coder is also a simplest one, where with single pass from each latent code Z, we are having our example within a single pass, so this is very fast.
Any other questions? Okay, so thank you, Michael, again.
Yeah, thank you.
Enjoy the break.